Hi everyone. So in this video, we're going to finish up our discussion of rational functions by talking about horizontal asymptotes. So the first thing that I want to kind of get out of the way is that a lot of students tend to get a little mixed up between horizontal and vertical asymptotes. And that's why I really separated them out and I talked about vertical asymptotes first in their own video, and we're going to talk about horizontal asymptotes now in a separate video. And it's really because even though they both have the word asymptote in their name, they're fundamentally different kind of features of a graph. So I'm going to be using in this video, again, as usual, HA and VA as abbreviations for vertical and horizontal asymptotes. But so here I'm going to say vertical asymptotes and horizontal asymptotes appear in graphs for very different reasons. Very different. So in the last video, we talked about vertical asymptotes, and we saw that vertical asymptotes, they appear when a function is undefined, right? And then we saw that sometimes there are holes instead of vertical asymptotes, but the important thing to know in general, the kind of general fact is that a vertical asymptote is only going to happen at an x value if the function is undefined at that x value, right? So vertical asymptotes appear at I'll say at some x values. Where a function is undefined. And I said some just because sometimes there are holes. But the important thing again is that vertical asymptotes have to do with the function being undefined. So what about horizontal asymptotes? What do those have to do with? So we talked a little bit about horizontal asymptotes in our first video, and basically horizontal asymptotes have nothing to do with a function being undefined. What they have to do with is the end behavior of the function. So horizontal asymptotes appear when the function has a certain type of end behavior. Okay, so what do I mean by that? Well, so first of all, remember end behavior was that thing where we talk about as x approaches infinity or as x approaches negative infinity, what happens to f of x. And so I'm going to write down kind of the definition of where a horizontal asymptote appears, and then we'll look at some examples. So a function f of x has a horizontal asymptote at a y value of a. So remember, vertical asymptotes happen at like x is equal to 1 or x is equal to -3 or something like that. Vertical asymptotes happen at x values, right? Because a vertical line has the equation x is equal to something. Horizontal lines have the equation y is equal to something, right? Because you're kind of saying, I'm just picking one specific height and looking at a line at that height. So horizontal asymptotes will always be in the form y is equal to a number. So when does a function have a horizontal asymptote at a particular height? Well, it's going to happen if as x approaches negative infinity, and then I'm going to say and or as x approaches positive infinity, and I'll tell you why I put the and or there in just a moment, the function approaches a. So basically what we're saying here, so if you think back to the type of end behavior we talked about earlier in the quarter, we talked about the function either going to infinity or negative infinity. Now we're talking about a function that instead of just getting bigger and bigger or smaller and smaller, it approaches a particular height. And then why did I put and or here? Well, for some types of functions, they might have a horizontal asymptote only on one side. For rational functions, it's always going to be the case that they have the horizontal asymptote both in the negative and the positive direction. So that's what you'll see in this video. But I just wanted to leave this kind of as general as possible. And that's why I put or, because when we talk about exponential functions, we'll see that there are functions that do have a horizontal asymptote only in one direction. So let me just rephrase this slightly. Another way of saying this is, in other words, if you have a horizontal asymptote at a particular height, what that means is that the function eventually levels out to a height of y is equal to a, right? Because we're saying instead of the end behavior being like f of x is going up to infinity or down to negative infinity, we're saying the end behavior is that the function is just approaching a particular y value. So let's look at some examples. And by the way, so the main focus of this video is going to be to learn how to find horizontal asymptotes without looking at the graph. So kind of like in the last video, we learned how you can just look at the formula and use that to figure out the vertical asymptotes and holes. Similarly here, we're going to find the horizontal asymptotes without looking at the graph eventually. But right now, I just want to kind of introduce you to what horizontal asymptotes look like in the graph. Okay, so this first one we've seen, right? This is 1 over x. And so we talked about how this one has a horizontal asymptote at y is equal to 0. And that basically tells us that when you plug in, just kind of looking at the graph, if you're trying to describe the end behavior, if you plug in a really big or really small x value, you can see that the function values, right, the outputs, the y values, are getting closer and closer to 0. The further and further you go out to the right, the closer that this red graph will level down towards a height of 0, and then the same thing out to the left. So not all horizontal asymptotes occur at 0. So here's an example of one that actually occurs at a height of -3. So if we put in this line at a height of -3, we can see that this graph, as x gets larger and smaller, eventually settles to this height at y is equal to -3. Okay, so not every rational function has a horizontal asymptote. So I have two examples that don't. So this first one on the left, we actually saw this one in our last video. So this was one where even though the function kind of looks complicated, it ends up actually, the graph just looks like a line with a hole in it, right? That's that comes from it being a rational function. That kind of tells us it's not just a line, it has something a little extra going on. But this has no horizontal asymptote, right? We do not see the graph flattening out to a particular height the way that we saw these ones flattening out. And then here's another example of a graph that has no horizontal asymptote. So this one kind of levels out towards almost looking like a diagonal line, but that's not horizontal, right? So this also has no horizontal asymptote. And so on these two graphs, the end behavior is actually going to be more like the end behavior that we saw earlier in the quarter with polynomials, right? So like, for example, on this green graph, as x approaches -infinity, h of x approaches -infinity, right? It goes down to the left. And as h of x approaches positive, or as x approaches positive infinity, h of x approaches positive infinity. And then on this graph, we'd say as x approaches -infinity, k of x approaches positive infinity, right? It goes up to the left. And then on the right, as x approaches positive infinity, the graph goes down, k of x approaches -infinity. So that does happen with some rational functions. They don't all have horizontal asymptotes. Okay, so the next thing we're going to do is we're going to look at a few examples of rational functions, and eventually we're going to come up with a rule that tells us how we can determine whether things have a horizontal asymptote or not. So don't worry, eventually there will be a concrete rule. But before getting to that rule, I want to kind of play around so that you can understand why the rules work the way they do. So what we're going to do with each of these functions is we're going to figure out what happens to the outputs of these functions, so f of x, g of x, and h of x, when x is very large or very small, right? Because we just said earlier that horizontal asymptotes have to do with the end behavior of a function. So if we don't know what the graph looks like, how can we like get an idea of the end behavior? We can do so by plugging in numbers. We did that actually, I think, with the polynomials. Before we learned the rules for what the end behavior was, we talked about plugging in numbers and how that is a way of determining the end behavior. So look at these three functions before we get started and notice that they're very similar. They all have the same denominator. And then the numerators are fairly similar. The only thing that's changing is that first term, right? So the first one is x minus 1, next one is 2x squared minus 1, next one is x cubed minus 1. So we'll see that just that small change of only this one term is going to be enough to change the horizontal asymptotes of these three functions. Okay, so let's start with f of x. So what I want to try is first plugging in 100. So I want to see what happens when we plug in 100, because that will give us kind of an idea of what happens when we plug in a big number. And then we'll also try plugging in 1,000 and then kind of use that to gauge the trend of where the function is going. So what does it look like if we plug in 100? Well, in the numerator, we'd have 100 minus 1. And in the denominator, we'd have 100 squared minus 5 times 100 plus 6. So I'm not going to completely simplify this because I want to kind of leave it written in this way to point some things out, but I am going to take this 100 and square it and kind of just clean up the denominator a little. So 100 squared would be 10,000, right? So when you take a number like 10 or 100 or 1,000 and raise it to a power, that multiplies your number of zeros. So 100 times 100 would have 4 zeros. And then we have minus 500 plus 6. Okay, so let's say that you didn't have a calculator and you had to kind of guess, like, what kind of a number is this? You know, looking at this fraction, is it going to be a really big or a small number? Well, it's going to be a very tiny fraction, right? Because what's going on here is that the denominator is way bigger, right? So you might look at this numerator and say, well, that's a pretty big number. 100 minus 1, that's 99. Like, that's a big number, and that's true. But in the denominator, we have 10,000. That has like 2 extra zeros compared to 100. And so even without paying attention to any of this or to this, if we just kind of focus on the numbers that have the most zeros, right, that would be this and this, we can already see that the denominator has so many more zeros, or I mean, it only has 2 more, but that's already a much bigger number than the numerator. And so basically this is going to be a fraction where you have a smaller numerator over a bigger denominator. And that will give you a number that is pretty close to 0, right? If you think of a fraction like 1/10 or 1/100th, those are very tiny fractions, very close to 0. And so if you were to type this into a calculator, you would see that this would be approximately 0.01. Okay, let's see what happens when we plug in 1,000. So in the numerator, we'd have 1,000 minus 1. So, you know, pretty big numerator. But then in the denominator, we're taking 1,000 and squaring it. And so that's going to actually give us a really, really big number in the denominator. And so in the numerator, we're going to have, you know, 1,000 minus 1. So that would be like 999. But then in the denominator, so when you take 1,000 and square it, you get 1,000,000 because you get 6 zeros. Minus 5,000 plus 6. So once again, without getting too specific about exactly what this number equals, you should already be able to tell this denominator is so much bigger than the numerator, right? 1,000,000 has 3 extra zeros compared to 1,000. And so this fraction is going to be even tinier than the one above it, right? Because again, just think of a fraction where the numerator is significantly smaller than the denominator. It's going to be a very small fraction. And so if you type all of this into a calculator, you'll see that it's equal to about 0.001. So what's happening? Well, the bigger the number we're plugging in for x, the smaller and smaller the result is, or maybe I shouldn't say smaller, it's getting closer to 0 specifically, right? We have 0.01, then we have 0.001. And so the general trend is that as x approaches infinity, right? That's kind of what we're testing here. We're testing out bigger and bigger x values. What's happening is that f of x is approaching 0. If we were to plug in 10,000 as our next result, we would get 0.0001. So the trend would continue. We would keep getting these huge denominators that are bigger than the numerator, and that will give us smaller and smaller fractions. And so we didn't do negative infinity, but I'll just tell you, you would see the same behavior as x approaches negative infinity. And if you want to try it out, definitely be my guest. You'll see the same kind of thing happening. And so what does this tell us in terms of asymptotes? Well, we know that if your function is eventually kind of leveling out to a particular y value, it has a horizontal asymptote at that y value. And so what we should see is that our graph should have a horizontal asymptote at y is equal to 0. So let's take a look at the graph and just confirm that we actually see that happening. Okay, so this was that function. So we can see, we can see that, this function has some vertical asymptotes, but that's not what we're worried about right now. We're just looking for a horizontal asymptote. And so as we plug in bigger and bigger values for x, we can see that the graph gets closer and closer to 0. And then the same thing happens with the negatives. Notice that on the left side, the graph is kind of starting below and working its way up towards 0, whereas over here it's starting above and working its way down. That doesn't really matter. When we're talking about horizontal asymptotes, we don't really care which side of that height the asymptote or the function is on. We just care that it's eventually getting there, that it's settling down towards that value. Okay, so I want to use this observation to kind of come up with a general rule, and then we'll see what we can find from these next two functions. So what was it about this function? Like, why was it that the denominator got bigger and bigger compared to the numerator, right? Because that's the thing that made this function level out towards 0. Well, if we look at the function, notice that the degree of the denominator is bigger than the degree of the numerator, right? And the numerator is just x, or x to the first power, whereas in the denominator, it was x squared. And so it was that squaring that caused the denominator to get bigger and bigger and bigger at a quicker rate than the numerator. And so we'll see that degree is really going to be kind of our key feature that will tell us whether a function has a horizontal asymptote at a particular value or whether it has no horizontal asymptotes. Okay, so for a rational function, so we're going to keep coming back to this page to kind of finish adding or add the different rules as we discover them. So for a rational function, f of x is equal to p of x over q of x. So remember in the first video when we talked about rational functions, I defined them like this, where I said it was a polynomial over a polynomial. And so I'm going to be using p of x and q of x to refer to the numerator and denominator, mostly just so I don't have to write numerator and denominator, because those are longer to write than p of x and q of x, right? So the first thing that we just found is that if the degree of the denominator, or actually I'll say it this way, if the degree of the numerator is less than the degree of the denominator, there is always going to be a horizontal asymptote at y is equal to 0. It doesn't matter what those degrees are. It doesn't matter what the coefficients are. It doesn't matter what else is going on in the function. It's always going to be true that if the degree of the numerator is smaller than the degree of the denominator, right? Degree, again, remember, means the highest power. It's always going to be true that we're going to have a horizontal asymptote at y is equal to 0. So from here on out, instead of, you won't have to go and plug in numbers like we did in this example. You definitely can. It's a good way to make sure you understand what's going on. But from here on out, you can feel free to just use that rule in order to determine whether something has a horizontal asymptote. Okay, so let's see what happens differently or similarly with this next one. So g of x was the same kind of function, except for that the denominator is the same. The numerator was 2x squared minus 1. So I'm going to put in 100 and try to get an idea of what this looks like. Okay, what was it? Plus 6. All right, so what does this look like if you start to multiply it out? Well, 100 squared, we already saw that that is 10,000. So in the numerator, we'll have 2,000 minus 1. And then in the denominator, we'll have 1,000 minus 500 plus 6. So just like before, it's really always going to be the highest power in the numerator and the denominator that really control what's going on. So just to kind of remind you, looking at these ones, these were really the only numbers we had to focus on to compare to see what was going on, right? Because these other numbers here just aren't going to have as much of an impact as these bigger numbers that have more zeros. And so similarly here, if we focus on this number and this number, now notice that they actually have the same number of zeros. So you can kind of think of finding the end behavior of rational functions as this kind of like battle between the numerator and denominator. So in this one, the denominator won, right? The denominator was the one that was getting bigger and bigger and bigger. And so that succeeded in kind of pulling the function down to having a horizontal asymptote at 0. In this case, they're kind of tying, right? I mean, the numerator is bigger, but if you think about just like the number of zeros, right? That's kind of like the magnitude of the numerator and denominator, they have the same number of zeros. And so what's going to happen is that this fraction is actually going to be pretty close to just equaling 2, right? Because these numbers here just aren't like really going to make a huge impact on the value. The numbers that are really going to control what this fraction equals are the 2,000 and the 1,000. So if you type this all into a calculator, you'll find that this is approximately equal to 2.1, right? So it's really close to 2 because it's almost like you're just doing 2,000 over 1,000. Okay, what about if you plug in 1,000? Let's see how this trend kind of continues. So if you do 2 times 1,000 squared minus 1 over 1,000 squared minus 5 times 100 plus 6. So this time we're going to get, again, so what was it? It was a million, so it's going to be 2 million minus 1 over 1 million minus 500, or sorry, this was supposed to have another 0, minus 5,000 plus 6. So again, there's a lot going on in this fraction, but really the numbers that are by far the biggest numbers in this fraction are this one and this one, right? The negative 5,000, I put, for some reason, a comma there. The negative 5,000 is not going to make a huge impact on a million, right? A million is a way bigger number than 5,000. And so again, we can predict that this fraction should be approximately equal to 2 because it's really going to be pretty close to being 2 million over 1 million. So if you type this into a calculator, you'll find that it's actually 2.01. Okay, so where is this function heading? The last one we saw, the outputs were getting closer and closer to 0. This time, they're not getting closer and closer to 0, they're getting closer and closer to 2. So this one is going to have a horizontal asymptote not at 0, but at 2. So we can see that as x approaches infinity, so as we plugged in bigger and bigger inputs, the outputs were getting closer and closer to 2. And again, we didn't do negative infinity. How did I say it on this one? I said, okay, same behavior. I'll say it this way, for x approaches negative infinity. Maybe let me say it this way. That makes a little more sense than saying as. But yeah, if you were to plug in numbers like negative 100, negative 1,000, you would see the same thing happening. And so what this one tells us is that we have a horizontal asymptote at y is equal to 2. So let's take a look at the graph to kind of see what that looks like. So this was our last one. Here is the new one. So we'll see that it does still have the vertical asymptote at 2 and 3, the way the other one did. But if we look at the horizontal asymptote, so what is the value that this graph is leveling out to? So if we go out to the right, we can see that the graph is getting closer and closer to a height of 2. And if we go in the other direction, we can also see that the graph is getting closer and closer to a height of 2. So we can see that we do have a horizontal asymptote at 2. Okay, so what's the deal if we're going to now kind of generalize this into a rule? What's that rule going to be? Well, remember, it's always about degrees, right? Because degree is what kind of tells you what's going to be the most significant part of the numerator and denominator. So what's going on with the degrees in this one? Well, in this case, the degree is the same, right? We had 2 for both of them. So where did that 2 come from for the horizontal asymptote, do you think? Like, why did the horizontal asymptote come out to be specifically the number 2? It doesn't have to do with the degree being 2, right? This 2 didn't really show up in the actual function. What it has to do with is this number and this number, right? 2,000 over 1,000 is approximately equal to 2. And so it turns out that when you have the same degree in the numerator and denominator, it's going to be the leading coefficients from the numerator and denominator divided by each other. And it's just for this reason. It's because the leading coefficients determine kind of what exactly are the 2 numbers you have here and here. And when you divide those 2 numbers, that will tell you what the function is approaching. Okay, so let's add that to our list. So second one we saw is that if the degree of p of x is equal to the degree of q of x, then you're going to have a horizontal asymptote at y is equal to a over b, where a is the leading coefficient of the numerator, so of p of x, and b is the leading coefficient of q of x. So it's basically just taking the leading coefficient of each of them and dividing them, and that will tell you where your horizontal asymptote is. Okay, so let's go back and do our last example, and then after this we'll do a few examples where instead of doing it by plugging in numbers, now we'll just go ahead and use the rules that we came up with. Okay, so the last function was x cubed minus 1 over that same denominator. Okay, so let's start by doing the same thing we did with the last ones. Let's start by plugging in 100. So that would be 100 cubed minus 1 over 100 squared minus 5 times 100 plus 6. Okay, so what is 100 cubed? Well, as I mentioned earlier, basically when you take a number that's just 1 and some zeros and raise it to a power, that tells you how many zeros you'll have. So if you do 100 cubed, that's going to have 6 zeros. So it's going to be 1,000,000. And so down here we'll have 10,000. Okay, so in this case, what is going on? What is bigger here in between the numerator and denominator? Well, in this case, the numerator is way bigger, right? The numerator is the one that has all the zeros. It's kind of like the reverse of our first example, right? In our first example, we had this denominator that was way bigger than the numerator. Now it's switched. Now the numerator is way bigger than the denominator. And so what's going to happen, what happens if you take a really big number and divide it by a smaller number? Well, you get a big number, right? And so if you type this into a calculator, this is approximately equal to 105.2. So it's not like leveling out. It's not, or well, we don't know that yet, but it's not, going towards 0. It's just a big number because the numerator is bigger. The numerator kind of won that battle as we plugged in a big number. So let's compare with 1,000. So 1,000 cubed minus 1 over 1,000 squared minus 5 times 1,000 plus 6. Okay, so the numerator is now going to be a very big number. So it's going to have 9 zeros. So what is that? Is that a billion? Okay, so that's our numerator, minus 1. And so now you can hopefully see why this minus 1 doesn't even matter, right? The number that is first is just going to be so much bigger. And then in the denominator, 1,000 squared is 1,000,000. Okay, so the denominator is still a big number, right? 1,000,000 minus 5,000 plus 6, that's still a big number. But a billion is like so much bigger, right? We have 3 additional zeros in the numerator compared to the denominator. And so when you divide this out, now we get that the answer is approximately 1,005.02. So what's happening? The bigger the number we plug in, the bigger and bigger the numerator is getting. And the denominator just can't keep up, right? The denominator just can't catch up with the numerator. And so then the results are just getting bigger and bigger and bigger and bigger. And so what does this tell us about our end behavior? It tells us that as x approaches positive infinity, h of x approaches positive infinity. Now for this one, if you did negative infinity, it would actually be the opposite way. So we didn't do this in the video, but if you wanted to try this yourself, if you plug in like negative 100 and negative 1,000, you'll find that the function will approach negative infinity. But that part doesn't really matter. You know, if the question is asking for the end behavior, well then yeah, you need to figure out which way it's going. But if the question is just whether the function has a horizontal asymptote or not, you know, that we can just say no, right? So if the function is not leveling out to a particular y value, if it's getting bigger and bigger or smaller and smaller, we can immediately say, okay, there is no horizontal asymptote. So let's take a look at what the graph of this one looks like. So that's this one here. So this one we can see when x gets bigger and bigger, it goes up to the right. When x gets smaller and smaller, it goes down to the left. And so we can see that there is no horizontal asymptote. The function does not level out and settle down to a particular value. So final rule we can put on here is if the degree of the numerator is bigger, so if the degree of p of x is greater than the degree of q of x, there is no horizontal asymptote. Okay, so these are basically the 3 rules we need to know. Why didn't I just tell these to you right away? Well, I wanted you to understand where they come from. So hopefully by plugging in the numbers in those examples, you got some insight into how these work, why they work the way that they do. But now that we have these rules, we can go and do some more examples without having to plug in numbers. So we're going to do these next 3 just using those rules. So we're going to find the horizontal asymptotes of each of these functions. Okay, so the key thing is just degree, right? We just want to look at the degrees. So in this case, the degree of the numerator is 2 and the degree of the denominator is 3. Right? So let's call p of x, we'll use p of x for the numerator and q of x for the denominator. So in this case, the degree of the numerator, p of x, is less than the degree of the denominator, q of x. And I'll put the numbers here, right? It was 2 was the numerator and 3 was the degree of the denominator. And so what do we know happens when the degree of the numerator is less than the degree of the denominator? Well, that's like the first situation that we had, right? That means that the function, the denominator is going to get bigger and bigger and bigger, and the numerator won't be able to keep up. So the function will eventually level out towards 0. So that will give us a horizontal asymptote at y is equal to 0. So let's check what the graph looks like and make sure that we see that happening. So that is, I think, this function. So we can see that, in fact, it does, right? It settles down towards 0. The bigger the x value you plug in, or the smaller the x value you plug in, the function levels out towards 0. Okay, so next one, we need to figure out if this has a horizontal asymptote, and if it does, what is it? So again, we want to look at the degrees, right? And so the degree meaning the highest power in the numerator and in the denominator. So in this case, the degree of the numerator is 7, right? And then the degree in the denominator is also 7. So we have 7 for both of them. And so what does this tell us? Well, this tells us that we have a horizontal asymptote, and to find that horizontal asymptote, we need to look at the leading coefficients. So here we have a leading coefficient of 5. Here we have a leading coefficient of -2. And so our horizontal asymptote is going to be at y is equal to -5/2. You could also write it as 5 over -2, but the kind of nicer way to write that would be -5/2, or -2.5. Okay, let's take a look at our graph. So that is this function. And so what we can see is that, so if we look out to the right, the graph looks like it's eventually hitting or getting closer to a y value of -2.5, right? Because this is -1, -2, -3. So it looks like it's pretty close to -2.5. And then same thing is happening out to the left. The graph is flattening out towards a level of -2.5. And one thing I just want to point out about this one is notice that in this one, we even have this like really big number of 100 here. Even if that was 1,000 or 1,000,000, that's not going to change things because it really just is the degree that determines what's going on. You could put a really, really big extra number at the end here and it still wouldn't be enough to throw things off because eventually you'll plug in a big enough number that it will be bigger than whatever that number is, right? Because especially in this case, it's like we're raising it to the 7th power. That's going to give you huge numbers pretty quickly. Okay, so last one, again, comparing the degrees. So in this case, the degree of the numerator is 4. And what is the degree of the denominator? It's 2. So the degree of the numerator is bigger than the degree of the denominator. And so what we saw happens in that case is that there is no horizontal asymptote. And so if you want to figure out in one like this what the end behavior is going to be, right? Because if there's no horizontal asymptote, there's a variety of ways it could look. And if you want to figure out how a specific function will look, that's where you would want to plug in some numbers to get an idea. But let's take a look at what this graph looks like, because this one is actually kind of different. So just to remind you, this was the other one we did with no horizontal asymptote. And this one had this kind of diagonal shape, right? If you like really start to zoom out, it almost starts to look like a diagonal line. But this one has a really different shape. So if I zoom out, instead of the sides kind of one going up and one going down, this one, both sides are going down. So it has different end behavior, but it's still kind of enough for our purposes just to say it does not have a horizontal asymptote. And by the way, if you're curious about these different kind of graph shapes where there's no horizontal asymptote, I am going to make a bonus video that is completely optional, but that you can feel free to watch to get a little bit more insight about the specifics of some of these graph shapes. All right, so that is it for rational functions. The worksheet for today, you'll be practicing with finding horizontal asymptotes as well as all the stuff from the last video. So it's a good chance to just kind of put everything together and make sure you still know how to do all the different features of rational functions. So I'll see you all in the next video.